Hi everyone, I'm back with the video for the exercises for the partial derivative problems from the previous video. I just want to comment on my formulation for each of the partials. What I wrote is the partial times dt or dn or dv because that truly is the change in pressure. That times dt. So for partial p, partial t, or how the pressure changes when we change the temperature, we have nRV dt. So we're taking the derivative of that with respect to T, treating the number of moles and the volume of our gas as a constant. If we do the same thing for partial P, partial N, so how the pressure changes when we change the number of moles, we're treating temperature and volume as a constant, getting RT divided by V dN. Volume is going to be a little bit different. If we look back at our equation, volume and pressure are inversely proportional. If we increase pressure, we're going to see a decrease in volume, and vice versa. That should be shown in our change in pressure contribution from changing the volume. So if we do the derivative of that with respect to V, treating N and T as both constants, we have negative N RT divided by V squared times dV. So the change in pressure is thus the sum of those three contributions, the change in pressure from changing each independent variable. Or the total derivative is thus the sum of the partials times their respective differential. Looking at the kinetic energy of the baseball, if we change the velocity, we would see a change in the kinetic energy of mv dv, where the partial of that with respect to v is just mv. Same thing for mass, we get v squared over 2 dm. And if we look at each of these, the units should give us energy. And they do. So then our change in energy is just the sum of the changes from changing both of the variables. The total derivative is mv dv plus v squared over 2 dm. Looking at our next example, the volume of a cylinder, we can think about it. So think of that pop can almost, and you're making it wider. You're increasing the radius of it. It's getting almost fatter. So then you could think of that piece as that shell times its change in R, or 2 pi r h dr, which should, if you had that shell and you cut it off the cylinder, you'd get this strip, this rectangular strip, that's 2 pi r length times the height with a thickness of dr. Since we made it bigger, we also increased the bottom increased and the top increased. So we should have that increase in those two volume pieces at the top and bottom, those little discs. Pi r squared dh, which you can imagine a circle or a new cylinder with thickness dh. That disc, pi r squared dh. So then the change in volume is thus the sum of both of those changes in volume. And if we think about the cylinder, we can picture each of those changes. Our next example was the potential energy of a spring. So if we look for partial V, partial K, so how is that potential changing when we change the spring constant? We have x squared divided by 2 dk. What if we change the displacement? We have kx dx. And then the change in the elastic potential energy would just be x squared divided by 2 dk plus kx dx. And lastly, our example with momentum, which would be one of the easier ones, is if we change the mass, we have v dm. We have that new piece of momentum. Or if we change the velocity, we have m dv. So then the sum of the total change in momentum should just be VdM plus mdv. It's another example of just the product rule if you wanted to do it that way. And that is all for this video. See you in the next one.